Hi, welcome everybody to my talk in this Mathematical Congress of the Americas Quantum Symmetry session. My name is Ana Ros Camacho. I'm a lecturer at Cardiff University in the beautiful country of Wales. And today, thank you to the organizers for the opportunity. I'm going to talk to you about algebra objects in group theoretical fusion categories. And let me point out that this work is joined with Yiby Morales from Los Andes in Colombia, Monique Mueller from São João del Rei in Brazil, Julia Plavnik from Bloomington in the United States, Angela Tabiri from Ames, Ghana, and Chelsea Walton from Rice University in the United States as well. So please let me start with giving you some motivation. Why are we interested in these algebra objects in categories that have a tensor product? To me, I have a very strong motivation for mathematical physics. And these objects, they actually appear in very interesting topics like conformal field theory, because in the particular case of rational two-dimensional conformal field theory, and as Fuchs, Runge, and Schweiger proved, they describe boundary conditions in these theories. But furthermore, they also have some realization in the context of vertex superior algebra extensions. One can prove that these extensions are one-to-one in correspondence with these algebra objects. This was shown by Huang, Kirillov, and Lipovsky, and promoted to supersymmetry. The vertex superior superalgebra context by Kreutzig, Kanade, and McRae. This is, of course, not an extensive list. There's many topics. Actually, one can argue why this is actually an interesting object. These are actually interesting objects to check. And today, I would like to focus in a very particular case of a category with a tensor product, which is the case of group theoretical fusion categories. These guys are related to many nice topics in mathematics, the representations of finite groups, semi-simple half-object algebras, and so on. But why these guys are like those, for me, the definite reason, it's because, they're a very good testing ground for any conjecture you may have concerning fusion categories. So it's like the place to go if you have an idea about something. Our target is actually describing Morita equivalence classes, representatives of algebra objects in these group theoretical fusion categories. And the nice thing is that we more or less had an idea about where to go, because there are some previous results by Ostrich and Natali. So just to put everybody on the same page, let me just tell you what I mean by fusion category and more things. So if I have a category and I put it in, I'm speaking, this is a sketch of a definition. I'm not going to be rigorous for the sake of the time, but let me just say that if we consider some tensor product in this category, so the category is monoidal, K-linear, meaning roughly that the homospaces are K-linear vectors or K-vector spaces, locally finite, meaning that these vector spaces, the homospaces are actually finite dimension. Abelian, there's a notion of kernel, co-kernel, and short exact sequence. Rigid, there exists a notion of duals, left and right, and also one more condition. If we we assume that actually the unit object with respect to the tensor product is a simple object, condition which is equivalent to say that the endomorphisms of this unit is actually isomorphic to the base field. If we have all these conditions, we will have what we call a tensor category. And if we include two more things, one, the category being, excuse me for that, the category being finite, meaning that we have finitely many semi-simples, up to some equivalence. And we have a semi-simple category, meaning that every object we have in the category can be written down as a decomposition, a direct sum of simples in this category. Then we will have what we call a fusion category. Our favorite example for today is going to be the following. The category of finite dimensional vector spaces, G graded, and of course over K. And the thing is, what's so special about this category is that the associativity constraint, notice this indexing here, is actually governed by some omega, which is a 3 cocycle. How does this act? On the symbols, if we denote the symbols of my category as delta G's, then the associativity morphism between these two going to this, it's going to be given by the identity times this 3 cocycle taking values on each of the labels of my symbols. Why this is like our favorite case is because the following fact. If we have a fusion category, and in addition, we assume that this category is pointed, meaning that, remember, we were assuming there's some dual objects. Well, with every dual, we need to specify evaluation, co-evaluation maps satisfying certain constraints. If we have that these evaluation, co-evaluation morphisms are isomorphisms, then we can say that our category is actually equivalent to this big G omega that we were talking about this previous example. Great. Once we are here, let me say what I mean by an algebra object. By this, I'm gonna be specifying a triple A, M, and U, where A is an object in my category. This M goes from 2 copies of A to A, the multiplication morphism. U is going to go from the monoidal unit to A, and this is the unit morphism. These two guys being morphisms in my category, satisfying associativity and unitality constraints in C. Yes, this is some kind of categorification of the notion of algebra. Example for following up from our previous example of vector omega. And some algebra we can define in this category is the following. If we consider, let me consider the so-called twisted group algebras, where, which is given by a bunch of copies of symbols, where L is a subgroup of my group, and in addition, the multiplication is not exactly what you would expect. You kind of tweak it with a Chuka cycle, related like this to the a Chuka chain related like this to the 3 cocycle. And this is how it plays the multiplication. Some, depending on the properties that these morphisms in the algebra have, you can have some, you can have some nice structures appearing. Example, let me find, if I take A in algebra, we want to say that this guy is a Frobenius algebra. If in addition to being an algebra, it's also a co-algebra, same definition, just reverse the arrows. And in addition, co-multiplication and co-unit, co-multiplication, multiplication, co-unit, and unit satisfy some compatibility conditions. For the X per I, it looks like something of this shape. I'm going to say that Frobenius algebra is special if composing multiplication and co-multiplication gives me the identity. So for the X per I, again, something like this. And if I compose unit and co-unit, I don't get exactly the unit, but unit times some non-zero element in my base field. Those examples I gave you just a second ago, the twisted group algebras, they actually satisfy these two properties. So as I said, this is some kind of abstraction of the notion of algebra over in, your linear algebra course. Actually, if you just carry on, in the same spirit, you can also define the notion of modules in categories. So just to be clear, if I have an algebra in my category, I'm going to define a right A module in this category to be a pair where a MPM, where my object, I mean, M is going to be an object in my category, and this PM denotes a setting action of my algebra on this object. So it goes from tensoring this object, algebra times the object, going to the object, and satisfying very similar associativity and unitality constraints as we will have in the usual definition of notion of module over a ring. Of course, I mean, I'm just defining here the right action. You can always go and define left modules and also AB by modules. Let me just, whenever I consider all of the modules I can have in one of these categories, I'm going to denote the category of all right A modules like this, all left modules like this, and all A and B modules like this. Actually, the group theoretical fusion categories, and a group theoretical fusion category is actually a fusion category that has this particular shape. So we're taking modules over our twisted group algebras, A bimodules. The tensor product is going to be given by the product over this algebra. This is going to be the unit, and associativity, and the rest of the structure morphisms are going to be just like in back G omega. When, of course, I'm following all the previous notation. K, I mean a subgroup. I mean beta will be a two cochain, and so on and so forth. Actually, why introducing this notion is useful, because with it, I mean this, and this on the long run is going to give us some extra properties of our algebras. I'm going to define a left C module to be an abelian. Remember, there's a notion of kernel, co-kernel, K-linear. This is set in structure on the home spaces, semi-simple. You can, every object can be decomposed as a direct sum of simples in your category, equipped with a certain bifunctor. This is, again, another categorification of the action of a ring over a module, of a module over a ring. And natural isomorphisms satisfying set incompatibility conditions. Why are we introducing these guys is because, well, I mean, exactly, if I consider the category of right A modules, this is actually a left C module. I know, confusing, but true. So why these guys are actually useful, I mean, to talk about properties of our algebras is because, in a way, you can talk about the properties of the algebra. I mean, going through these categories. So we say that an algebra A is indecomposable and respectively semi-simple if CA, remember, left C module category, is an indecomposable respective semi-simple abelian category. And this allows us to define the notion of Morita equivalence in our context. We say that two algebras in a certain category are Morita equivalent if their respective categories of right A modules, A and right B modules, are equivalent as left C module categories. This is all the background I needed to tell you. And now let's go to our results. Let me first stop by this. There was this result from Ostrich and Natali that we wanted to promote to group theoretical fusion categories. It says something like every Morita equivalence class of indecomposable semi-simple algebras in vector omega is actually represented by a twisted group algebra. That example was not innocent at all. Where the notation, I'm just following same as before. So what did we do to lift this into the case of group theoretical fusion categories? First, we took, we constructed the following functor. Let me take a special Frobenius algebra in a tensor category D. I'm going to denote this Frobenius algebra as A, that I forgot to include it. Well, one can show that actually this, if one defines a functor between this category and its category of AA bimodules, there is actually a monoidal structure on this functor. And actually, I'm skipping it for the sake of time, but this functor really behaves really well and preserves quite a lot of the properties of the algebra, including Frobenius. So our theorem, and notice the similarity from the previous one. Every Morita equivalence class of indecomposable semisimple algebras instead of vector omega, group theoretic fusion categories, is represented by a so-called twisted Hecke algebra. We baptize it like this because there's a double coset counting for the simples, and this is, kind of what it's used for these cases. So these twisted Hecke algebras are going to be defined by the image under this functor of my twisted group algebras, and we're going to denote it like this. And how do we prove this? Well, first we need to introduce the notion of Morita preserving functor. So some notion of functor, nice enough. So your Morita equivalence classes in one category are transported, all the way to the other the target category. And once we had this notion, we proved that our functor phi, something as nice as, as nicely defined as this, is actually of this kind. So we could go from equivalence classes, Morita equivalence classes in vector omega to the case of group theoretical fusion categories. So if I got your curiosity, for more details, please have a look at our paper that's posted on arXiv. But for now, thanks for watching the Elfin Found, as we say here. And if you have any questions, please don't hesitate to drop me an email at roscamachoa at cardiff.ac.uk. Thanks for watching.